Okay. So, good evening, everyone. It is my distinct pleasure today to introduce Professor Matthew Kunz from Princeton University. Professor Kunz got his bachelor's degree in physics with a minor in music, may I say, from the University of Virginia in 2003. Then he moved to the beautiful state of Illinois to get his, where he got his PhD in physics from the University of Illinois in Urbana-Champaign in 2009. And then he moved to across the Atlantic, right, to Oxford, where he spent 3 years as a postdoctoral fellow, to return back to the States with a prestigious Einstein Fellowship from NASA to Princeton. He liked it so much that he couldn't leave, so he stayed there as a Spitzer Fellow after his NASA fellowship expired, and eventually joined the faculty in 2015, where he's still an associate professor now. Professor Kunz is an expert on plasma physics, and among his many awards, got an NSF career grant, career award, and also he's also a Sloan fellow, right? So today he will tell us about the exciting and secret, mysterious life of Alfvén waves, and how they are self-defeating but also self-sustaining. So Matt, without further ado, you have the floor.
Great. Thanks so much, Chris. It's really a pleasure. Well, it could be more of a pleasure if I were there, but it's a pleasure to be speaking to you from my room. So I know this is a physics colloquium, so while I'm a plasma astrophysicist and plasma physicist and astronomer, I decided to focus this talk on just really basic physics. So I'm going to give an introduction from the standpoint of somebody that knows little about plasma physics, but is sort of approaching it from first principles. I'm happy to take questions during the talk, so please interrupt. I won't be monitoring the chat if you put it there, but you're welcome to interrupt. Great, so I'll explain what the title means when I get to it. For now, I just want to acknowledge the people that this work has been done with. It's John O'Squire down in New Zealand, which is paradise right now. Alex Shekachikin in Oxford, Elliot Quadert, who's now at Princeton, where I am, Lev Arzamovsky, who was a student who graduated last year, is now at the Institute for Advanced Study, and Archie Bott, who's a postdoc in the group. All right, so like I said, it's a physics colloquium, so let's start at the beginning. Imagine that you have a large collection of charged particles, large meaning that the number of particles in a device sphere is large. Pretty much any plasma, astrophysical plasma is in this category, so that's fine. So imagine a statistically large collection of charged particles and put them in a magnetic field. And from the standpoint of just basic physics, you've got a few options for how to go about developing theory. One is sort of brute force, right? So you write down a distribution function, which is not probabilistic at all. It just says, I have a particle of flavor alpha, so ions or electrons, at some position big R with some velocity big V, and you populate your phase space with these ions and electrons, which is described like that. And you say F equals ma for these particles. Of course, all these charged particles generate electric fields and magnetic fields, which are appended with M, which just means microphysical, because they have to do with the point particles. And you can take those two, and instead of solving this single set of equations, which is 6 dimensions for every single particle, so 6n equations, you can solve a single equation, which is 6n dimensional. And this is called the Kleeman-Tovich equation. And of course, you need to figure out what the electric and magnetic fields are. So you couple them to Maxwell's equations, which tell you that like point particles carry some current and they're distributed in phase space, and they carry some charge density, and then you just solve these things. And that's it, right? So that's plasma physics. Of course, there's problems. It's extremely impractical to do this for the number of particles in a real plasma. For every molecule in the room that I'm speaking at this precise moment, you need 10 to the 17 terabytes if you want to store their positions and velocities at double precision. It's a lot of data. It's also arbitrary. The system is very chaotic. So the initial conditions are arbitrary, since there's microscopic sensitivity to those initial conditions. It's also unnecessary, because in the end, you're concerned with bulk properties, observables, collective behavior, things that don't have to do with a bunch of delta function point particles. So what one could do from there is formulate non-equilibrium statistical mechanics of the system. So you take your this distribution that I gave on the last slide, and what you do is you consider the positions and the velocities of all these charged particles to be random variables, and you do an ensemble average or a Liouville average. And the idea is that instead of having a single realization of the system with definite capital R's and definite capital V's, you treat these R's and V's as random variables, and you pretend that you do this experiment many, 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 many times, and you compute expectation values of each individual realization of the system. And this gives you a statistical treatment. And so you see on the right, now the phase space is more coarse-grained, because this averaging procedure in practice coarse grains over all these point particles to make a smooth distribution, which is now a probability distribution. And there's a few assumptions that you have to make, but eventually you get it into this equation where F evolves because the particles carry information about F around with them at some velocity. And those particles are accelerated through phase space through these coarse-grained electric and magnetic fields, which are governed by Maxwell's equations. So this F is the likelihood of some particle being somewhere. It's not a particle being somewhere, it's just the likelihood of some particle being somewhere. And of course, correlations are formed through electromagnetic fields and Coulomb interactions, and those appear on this right-hand side. So this is called a collision integral. And this accounts for all the correlations between particles that are formed through binary Coulomb interactions. So in general, this thing is called the Bolesco-Lenard collision operator. Simpler version is called the Landau collision operator. And then, of course, you just close them with Maxwell's equations. So the nice thing about this, it's much cheaper, of course. You're not solving 6n dimensions for each species. You're just solving 6 dimensions. But even with today's computer power, it's still computationally expensive, mainly because, yes, it is 6-dimensional, but the problem is that a lot of frontier problems in plasma physics involve a very wide range of scales. And you have to, if you're solving this, you've got to resolve all of them. So Debye length, some skin depths in the plasma, some Larmor radii, gyro radii in the plasma, and some large scales where the dynamics occurs. It's also analytically intractable to deal with all this, except in very special circumstances. So what's usually done is you exchange that 6D phase space for 3D by taking moments of your distribution, computing the expected number, expected number of particles, the expected velocity of the particles, the expected sort of dispersion of random velocities of the particles, and you call these things the number density, the flow velocity, the pressure tensor, and so on. But the problem is, going down to 3 dimensions isn't for free. you have a situation where the density depends on the flow depends on the pressure depends on the heat flux, and so on. And you have this infinite hierarchy of moments. So you got to close this, and there's a variety of ways of closing this hierarchy. And one very well-known rigorous way is called the Chapman-Enskog expansion. The idea being that if the collisional mean free path is small compared to all the length scales that you're interested in, then you can prove that to leading order, your distribution function is just a Maxwellian with some number density, with some flow velocity and some temperature characterized by a thermal speed. And your distribution has a small deviation from this, which is small in a mean free path over L. And from that, you can obtain a closure. So you can express this pressure tensor here in terms of the lower moments. So in terms of the velocity, and there's some collision frequency associated with that mean free path. You could also write down a closure for the heat flux in terms of the lower moments, like the temperature. So that's all well and good, because now you've got a closed system of equations. And this is the option chosen by most astrophysicists who are interested in astrophysical fluid dynamics, usually in the limit that the mean free path shrinks to 0. So this limit, this is just standard ideal magnetohydrodynamics, MHD. It's simple, it's 3D. You've closed your hierarchy to just 3 moments. It's inexpensive because of that. And it's also rigorously justified in some cases. So like stars, some types of accretion flows, some phases of the interstellar medium in our galaxy and in other galaxies. You can go even further. A lot of these systems are magnetized, meaning that the gyro radius of a particle, an ion or electron, is very small compared to the mean free path in the typical macro scales that you're interested in. And in this case, that collisional transport, which is giving you one part of the pressure tensor and the heat flux, becomes anisotropic with respect to the magnetic field directions, B hat. So this is due to Brzezinski, so it's called Brzezinski MHD. And pictorially, this is what's going on, is that if I have a cold fluid element on one field line, and the gyro radii of the particles inside that fluid element are really small, these particles can free stream along the field, no problem. So there's no Lorentz force along there, until they encounter a mean free path. And if a hot fluid element is a mean free path away, there will be a heat exchange between the particles and the fluid elements. That won't happen, or it's at least much reduced transport across the field, because the smallness of the Larmor radii stifles collisional transport, because these particles can only deviate a Larmor radius off this field line, not a full mean free path. So what that does is the formulae that I showed you on the last slide for pressure and for the heat flux just acquire these B hats, so the magnetic field direction, which tells you that only certain components of momentum can be redistributed, only certain components of the heat can be redistributed based on the magnetic field. So there's a problem with this, is that many astrophysical and space plasmas that are magnetized, they either have mean free paths that are comparable or even larger than the macro scale systems, in which case departures from local thermodynamic equilibrium are large, and this whole procedure of going from this Kleeman-Tovich distribution and doing the averaging, taking moments, cutting off this moment hierarchy, that whole procedure isn't justified. Or it is justified, the mean free path is small, but this ratio of mean free path over macro scale is bigger than 1 over the plasma beta. So it's bigger than the magnetic energy divided by the gas pressure. So in this case, departures from local thermodynamic equilibrium, so departures from the Maxwellian distribution, are small because the mean free path is small. But it turns out in this case, these deviations are still large enough to cause the plasma to be unstable to very rapid instabilities on Larmor scales, and those instabilities end up breaking the hierarchy that you were using in the first place. And so more on this later. just to put out a flag that there are many situations in which that procedure does not lead to a suitable set of equations. So I'll introduce you to three such plasmas that satisfy this sort of broken ordering. Solar wind, certain classes of black hole accretion flows called low luminosity accretion flows, like Sag star at the galactic center, and the intracluster medium of galaxy clusters. So if you're not an astronomer, I'll tell you exactly what all these systems are. So we'll start with the solar wind. So the sun leaks about 10 to the minus 14 solar masses off of it per year in a wind. A typical velocity of this wind, which you're seeing on the right from SOHO, is about 400 kilometers per second. It ranges between like 100 to 800, something like that, kilometers per second. There's like a fast wind and a slow wind, but this is just the typical speed. And if you put spacecraft up around the Earth and you start collecting information at 1 AU, you get a number density of 10 particles per cubic centimeter, temperatures about 10 keV, so 10 to the 5 Kelvin, magnetic fields of about 50 microgauss. For reference, the Earth's magnetic field is about half a Gauss. So, so what you do is you pull up some formulae, you compute the collisional mean free path based on Coulomb collisions, and you find out that, it's an AU. So on average, a proton leaves the solar corona and interacts with, gets deflected by 90 degrees just once between the solar corona and the Earth. So it's weakly collisional. It's very well magnetized. So the gyro radius of an ion is 6 orders of magnitude down from the mean free path. And that corresponds to a cyclotron frequency, which is about a hertz. Okay, so the second thing I wanted to tell you about was black hole accretion flows. So if you go to the galactic center, there's a 4 million solar mass black hole. This is glowing plasma in the X-ray measured by the Chandra X-ray Observatory. In the innermost, roughly 3 parsecs of the galaxy. And if you go out, right, so the Schwarzschild radius of this black hole is about 0.1 AU. And what's called the Bondi radius is about 0.1 parsec. So this is where the sound speed equals approximately the escape speed for this black hole. So anything within a Bondi radius you can think of as being bound if it's thermal gas. So at that distance, we've got a number density of 100, so a bit denser than the solar wind. Quite a bit hotter at 2 keV, and a milligauss magnetic field roughly. And you compute various plasma parameters from this, and you find that dynamical times, like orbital times, is something like 200 years. The time it takes for an ion to collisionally interact with another ion through Coulomb interactions is about 20 years. So again, it's weakly collisional. And the gyro time for an ion to gyrate around this microgauss or milligauss magnetic field is, again, it's about a hertz. So these are drivable distances. You can drive an ion along the orbit in about 2 hours. It's extremely well magnetized. If you get within about 10 Schwarzschild radii, this is not Sag star. You've seen this before, hopefully. This is M87 from the Event Horizon Telescope. But if you get within about 10 Schwarzschild radii of the galactic center, this time scale hierarchy between the dynamical time and the collisional time is completely inverted. Dynamical times are like 10 minutes, but the collision time is like 200 years. So it's a completely collisionless system. And again, it's strongly magnetized. So the gyro time of an ion is 100 microseconds. So very well magnetized collisionless plasma. And finally, galaxy clusters. So galaxy clusters are the largest realized objects in the universe. You're seeing a typical relaxed galaxy cluster on the left in the optical. So you see all these galaxies within about a megaparsec volume. And I've centered here in the innermost 200 kiloparsecs where there's what's called a central dominant galaxy. And the reason why it's sitting there is because most of this 10 to the 14 to 15 solar masses in a galaxy cluster is in the form of dark matter, something like 84% or so. And that galaxy right there is sitting in the the bottom of the potential well set by this dark matter. If you're a plasma physicist, you don't care about any of that, except that there's a bunch of X-ray emitting plasma sitting in this potential well, feeding these galaxies slowly. This is called the intracluster medium. So about 14% of this mass is in the form of this X-ray emitting plasma in the 1 to 10 keV range. So it's emitting by Bremsstrahlung. It's quite diffuse, and so this the emission is low, so the cooling time is really long. In some cases, once you get outside of 200 kiloparsecs, the cooling time here is longer than the age of the universe. That's because of these low number densities. And we also know from some Faraday rotation maps that the magnetic field is measured in microgauss. And then the Hitomi spacecraft, just before it ceremoniously died, after just 2 observations, told us that in the Perseus cluster, a nearby cluster, there's turbulence, which is subsonic. So the sound speed here is about 1,000 kilometers per second. So this is subsonic turbulence. And again, you convert these things to something that a plasma physicist would care about, and you get dynamical times of 100 million years. So this is like a buoyancy time in the stratified plasma. Collision times between ions are 1 to 10 million years. So it's just, again, weakly collisional. There's not that much scale separation between the macro scales and the collisional scales. And then all the way down here at about the size of Jupiter inside of a megaparsec volume is the ion gyroradius. So very, very strongly magnetized in that regard. So all these plasmas are strongly magnetized. They're weakly collisional. And one would like to have a set of equations that one could describe short of solving the full kinetics with Maxwell's equations. And that task is made complicated by a few things. One of the things it's made complicated by is the strong magnetization. The other thing is that despite the strong magnetization, these plasmas have a high beta, meaning the gas pressure divided by the magnetic pressure is order 1 or bigger. And that presents some problems, which I'll get to. But just to express why this is important, most of the baryons in the universe are in this hot phase. And even though this is widespread in the universe, this state of matter remains poorly understood. We lack a complete predictive theory for how it responds to perturbations, how it transports momentum, how it transports energy, how it generates and amplifies and sustains the magnetic fields that we see. To a plasma physicist, these questions just have intrinsic interest. To an astronomer, there's a lot of applied interest, because if you sort out those sort of questions about transport and turbulence and magnetic fields, you can address a lot of questions that are raised by space and astrophysical systems. So I put some of those questions here. I'm not going to talk about any of these questions. This slide here is just to emphasize that despite these different systems, they basically all have multi-scale plasma dynamics resting beneath all these astronomically motivated questions. So how is heat transported? What instabilities and fluid instabilities and kinetic instabilities are there? How do they drive turbulence? Does that turbulence facilitate momentum transport? And so despite these various different questions and these very different systems, there's a common theme, which is that we just don't know the material properties of this type of gas, this type of plasma. We don't know the effective collisionality, the viscosity, the conductivity, the resistivity, how wave-particle interactions play into this, since the particle-particle interactions are very rare. So in a simple question, and this is what I'll try to address a piece of in this talk, is because these systems are poorly collisional, you expect departures from local Maxwellians. I will talk about how these departures induce kinetic physics, important kinetic physics occurring at small scales, and how that kinetic physics affects turbulence, transport, heating, and ultimately global dynamics. I will not talk in this talk about global dynamics or heating or transport or turbulence. I'm going to talk about something much more fundamental that feeds into all these things, which are just simple waves. But this whole procedure is part of a broader goal of because full 6-dimensional kinetics is too expensive to solve a lot of questions in these systems, one would like to formulate an appropriate set of equations which are reduced, that are manageable, that you can put on a computer, that you could do some theory with, but still accurately describe all this multi-scale plasma physics, which at its heart really deserves to be treated as a 6D kinetic system. Good. So that's the sort of motivation intro, just a bit long. This is some physics background that you'll need for the rest of the talk. And so what makes answering these questions difficult is basically two things. The fact that the system's magnetized, so these non-Maxwellianity in the system has some respect for the local magnetic field, and the fact that these systems are high beta. So I'll explain what I mean by each of these in the next few slides. So first, just this one. So suppose I have an isotropic Maxwellian velocity distribution of my plasma particles. So this would just be a distribution function, which goes like e to the minus v squared over temperature. And if I were to slice this, spherical distribution in slices and plot isocontours, it would look something like this. And I've been saying that these systems are very strongly magnetized, where the Larmor radius is very small. So let's thread this plasma with a magnetic field. And that plasma, now that it's magnetized, has a very natural coordinate system, which is anchored on the magnetic field direction b hat. So you can rewrite this distribution function in terms of v parallel, so parallel to the magnetic field locally, perpendicular to the magnetic field locally. And because the distribution here is still isotropic, both v parallel and v perp are normalized to the same temperatures. Now, also because the system's magnetized, you've got adiabatic invariants in the system. So what this means is that there's some periodic motion induced by the magnetic field. So one is, of course, just Larmor gyration, is periodic motion. And if you change the magnetic field strength slowly, there's an adiabatic invariant, which is the perpendicular energy of the particle divided by the gyro frequency, just like every adiabatic invariant, just energy divided by a frequency. And as you dilute that magnetic field, the Larmor radius has to adjust adiabatically. You can also think about it in terms of Lenz's law. It has to conserve the amount of magnetic flux through its Larmor orbit. If you have a magnetic bottle like this, there's also periodic motion as the particle bounces back and forth inside of this bottle. It's like it's rolling down the hill and then up the hill and then back down. Essentially, there's a force on the guiding center of the particle, which knocks it back and forth. And if you change the length of this bottle slowly compared to that bounce time, there's also an adiabatic invariant, which is called J, which is called the balance invariant. And if you take these mu conservations, so this magnetic moment conservation and this bounce conservation, and you average it over the entire plasma population of particles, the distribution function changes. So for example, if I took that isotropic distribution in this v parallel v perp coordinate system, and if I decrease the magnetic field, the distribution function will be distorted like this to acquire excess parallel energy. And it's because if B goes down, V perp has to go down by mu conservation. So the distribution function ends up looking something like this. Likewise, if you take that isotropic distribution and you increase the magnetic field and you conserve these adiabatic invariants, your distribution function is going to end up looking something like that. So in both of these cases, you have this exponential where there's minus V parallel squared and a minus V perp squared, but now the temperatures are different. And this difference between the temperatures along the field and across the field is referred to as a pressure anisotropy. And this pressure anisotropy is ultimately what's responsible on the macro scale for the viscosity of the plasma. Good. Such field bias distortions are measured in the solar wind. So like I said, the solar wind is a collisionless plasma. There's no reason for it to be Maxwellian. You can put spacecraft up at a variety of distances from the sun and measure particle distribution functions with a Faraday cup and measure magnetic field directions with a magnetometer. And lo and behold, these distributions have excess perpendicular energy. See the T-perp, so the thickness of the distribution across the field line is bigger than it is along the field line. You also have some non-Maxwellian features like these beams that are oriented along the magnetic field direction, things like that. Okay, so that's these field bias departures and now high beta. So why these departures matter at high beta is that if these departures are big enough, they cause all sorts of microscale dynamics. So again, if I take an isotropic distribution and I increase the magnetic field and I conserve these invariants, my distribution function will look like this. And if those distortions are bigger than this dotted line, so mathematically, if the parallel pressure minus the perpendicular pressure is fractionally bigger than the magnetic pressure, basically, you get something called the fire hose instability, where the magnetic field grows to have these really sharp crinkles in it on gyro scales for the ions. Likewise, if you increase the magnetic field and the distribution function looks like this, there's also a threshold that limits how big the perpendicular pressure can get. And that's something called the mirror instability. And I'm not going to dwell too much on the details of how these instabilities evolve and saturate. You can find that in this paper. There's really just two things I want to emphasize right now is that, so departures from a Maxwellian will excite these rapidly growing ion Larmor scale distortions in the magnetic field. And ultimately, particles are trying to gyrate around a field that looks like this, and they get scattered because they don't know which direction the field is pointing. And also particles can get trapped in these magnetic bottles. And so they're not able to just stream along the field line anymore because they get trapped inside these magnetic bottles. And the important part of high beta is that this number, suppose I went to the intercluster medium, beta is 100. This number is 1%, 1%. So you only require 1% deviations from an isotropic Maxwellian for these instabilities to be triggered and to grow really rapidly, like on cyclotron frequency timescales, and distort your magnetic field. These instabilities have been observed in the solar wind. I'm going to skip this slide and just return to the question which we originally had. And so my group has a whole program of work on this topic of diagnosing the material properties of high beta plasmas and understanding dynamo and understanding turbulence and transport. But for the purposes of this talk, since it's a physics colloquium, and I'm not going to assume much background in plasma physics, I just want to focus on the simplest examples that I have of interesting physics that occurs in these kinds of plasmas. And that concerns just very simple wave propagation. How an Alfvén wave propagates in this high beta collisionless plasma, and how a sound wave propagates in this high beta collisionless plasma. And if you're interested, the papers are here. Good. So first, an Alfvén wave. So let's start with a very simple thought experiment. Suppose that I have a magnetic field line. It's just been handed to me and it's bent. The magnetic field lines don't like being bent. They want to straighten out. And if I embed this bent magnetic field in initially Maxwellian collisionless plasma, it's going to want to relax because there's some tension in the magnetic field. And as it relaxes, it'll eventually oscillate back and forth because it'll pull the material with it. The material has some inertia, and then that'll make it oscillate back and forth at what's called the Alfvén speed. But what I want to do is not pay attention to the whole oscillation. I just want to pay attention to what happens to the distribution function as I let this magnetic field straighten out. So I've got a bent field. I start with a Maxwellian, and I let that field straighten out under its own tension. And I can ask just a simple question in this quarter of a wave period, how much pressure anisotropy was driven just because the field strength decreased as I went from a bent field line to a straight field line. It's a very simple calculation that you can do based on these adiabatic invariants. I'm just going to ignore this last expression, just concentrate on the collisionless case. So the magnetic field changes by an amount of delta B, which was the fluctuation. And this is how much pressure and anisotropy I would expect just from the field line straightening out. And then you can ask the question, when is this pressure and anisotropy dynamically significant? When would these departures from local Maxwellian actually affect the macro scale evolution of this wave? And it's exactly when this criterion holds, which you've seen before. This is this fire hose criterion. And right at this moment, there's a viscous stress, which is associated with this pressure anisotropy. And at this moment, that viscous stress is competitive with the magnetic tension, which is trying to drive the wave in the first place. And so you've got this threshold here, where if I have an Alfvén wave, a magnetic wave, where delta B over B is bigger than 1/square root of this plasma beta, in this situation, this wave as it oscillates will be distorting the distribution function in such a way that those distortions will ultimately combat the magnetic tension, and the wave will not propagate. So I'll show that in the next few slides. So this is just saying what I just said with some mathematics. This is an equation for the inertia of the material. So the acceleration of a fluid element has to do with the magnetic tension, which is there, and also this viscous stress, which has to do with P parallel. And you can see that this magnetic tension, which is responsible for driving the wave, can be exactly offset by this pressure anisotropy that self-consistently drives by itself. So if this is able to get large and negative, it can compete with the magnetic tension, which is trying to drive the wave in the first place. And if that happens, the wave nonlinearly removes its own restoring force and can't propagate. So I'll show a movie of this on the next slide. For now, I'll also note that at that threshold, the plasma will explode in a sea of unstable gyroscale fluctuations, these fire hose instabilities, which scatter the particles and decay the wave. Okay, so to show you an illustration of this process, first I'll show you what an Alfvén wave looks like just in MHD. So no pressure anisotropy, just a boring magnetic oscillation. And to orient you, here's a long box along which there's a guide field. And the color that you see is delta BZ, which is out of the plane. So the field is distorted to be out of the plane here and into the plane there and there. And I've set up a standing Alfvén wave here. So if I just let it go, the tension will relax the field. The inertia will make it overshoot its equilibrium position, and it's just going to oscillate back and forth. So now I'm going to do that same calculation, but in a kinetic code, which involves a collisionless plasma. So up here on the top panel, this will be the equivalent to what you just watched. There's a guide field along this direction. This box is 1,000 Larmor radii long. So this is a long wavelength shear Alfvén wave. And what you're going to see is also some dynamics occurring in another component of the magnetic field, which nothing should occur if it were just MHD. And then down here is a measure of the pressure anisotropy, which you see it's yellow, which means 0. So I initially start with the Maxwellian. What you're going to see when I play this movie is the system's going to become not Maxwellian, and eventually it's going to be unstable. So let me go ahead and run this. And you'll see this top panel behave similar to before, where the magnetic field just relaxes. So the field relaxes, but as it relaxes, the pressure anisotropy goes negative. And then eventually it passes this -1 threshold, and you get all the small scale stuff, which are these fire hose fluctuations. And if I let the movies keep running, you'll see that this Alfvén wave is not a wave. So it's removed its restoring force because this viscous stress balances the Maxwell stress. And it should have oscillated up and down by now, but instead it just sits there and decays, which is neat. This is an illustration of what such an Alfvén wave would look like as it's traveling. So it travels, it excites all this small scale stuff. And before one period is up, it's slowed way down and decayed a lot. So none of that would happen in just a collisional MHD plasma. So this is significant because almost all of plasma physics is based on Alfvén waves as a fundamental building block of the dynamics. And we found that just Alfvén waves can't be sustained if their amplitudes are bigger than this 1/√beta threshold. And this is important because in a lot of these systems, beta can be 100 or 1,000. So this is a small number. So even a small amplitude wave is completely screwed up from what MHD would predict. So that's it for Alfvén waves. And I want to play this game also with sound waves. So consider a small amplitude sound wave. In a magnetized weakly collisional plasma, it's very easy to write down a dispersion relation for this Alfvén wave. So the frequency is related to the wave number by the sound speed. We'll call it A. Doesn't matter what it is. And you might have some viscous damping of the wave. So except for these viscous losses and any nonlinear steepening of the wave that might occur, sound waves propagate just fine in a fluid. Well, I guess you know that because you can hear me. If I were speaking in a collisionless plasma, you would not hear me. So the dispersion relation for a sound wave in a collisionless plasma looks like this. This thing is called the plasma dispersion function. It doesn't matter what it is. The point is that this equation tells you that the wave is going to decay in one wave period. So the decay rate of the wave is equal to the frequency of the wave if the ion electrons have similar temperatures. And this is something called Landau damping, which if you've not seen before, here comes a Greek boat, which is executing Landau damping on a wave. If you're in a boat and you're riding a wave, you extract energy from that wave if you're resonant with the velocity of that wave. So I want to go through that whole process now, but for a weakly collisional plasma in which the distribution function can get distorted due to adiabatic invariants. So again, start with an isotropic Maxwellian distribution. And what you'll find is that regions where the sound wave decreases the local density have the distribution function distorted in this way. And regions where the density increases have the distribution distorted in this way. And if the pressure anisotropy gets over these thresholds, again, you get these fire hose and mirror instabilities. And why that matters is because when you learn about Landau damping, I suppose it's not about Greek boats on waves, but it's normally some kind of surfer, which is resonant with the wave and extracting energy from that wave by being resonant with it. And the process is more like this, because these particles are going to be trying to be Landau resonant with the sound wave and damp that sound wave. But there's going to be all this small scale magnetic jitter. And instead of this nice smooth wave that it's riding, it's going to be riding on top of all this jitter, and it's going to have a hard time maintaining resonances. So again, we got a kinetic simulation, and the first thing that we did was just set up a sound wave that should oscillate and Landau damp. So this is the density fluctuation versus time, RMS, and it just oscillates and Landau damps at the correct rate. But if you put a magnetic field in there with a plasma beta, which is high, like 100, and you do this again, the wave starts Landau damping and then stalls. And on the next slide, I'll show a movie of exactly why it's stalling. And it's precisely because of all this small scale magnetic turbulence that the particles are getting kicked all over the place. And so what you're going to see here is a box which is extended in the x direction along a guide magnetic field. You see this is 1,000 rho, so it's 1,000 Larmor radii long. And what's going to be in these plots is the pressure anisotropy. So it starts at 0 because I'm starting with an isotropic Maxwellian into which I'm putting a sound wave. And these are 3 magnetic field components, which if it were just an MHD sound wave should do absolutely nothing because it's just a sound wave. And as I play the movie, you're going to see a line appear here and start at 0, and it's going to go into this fire hose region and into this mirror region, and you're going to see an explosion of magnetic field fluctuations in these regions. So there, And these magnetic fields grow extremely rapidly and deplete the pressure anisotropy. It's trying to keep the system stable by transferring some of that free energy and the anisotropy into the magnetic field. And now you've got all these field fluctuations that these particles have to navigate through. And it's very difficult for them to do so. And you can see that. So in this slide, you could just ignore this top panel and concentrate on this. So this is the box along the x direction. That's the guide field. And this is time. So space-time diagram. And inside of the space-time diagram, the color is the local collisionality. So you can follow the particles and you can see how often they just scatter their pitch angle because they've scattered off of some magnetic irregularity due to these instabilities. So you can follow these particles through the box. And at first they just free stream like they should. And then they encounter a region of fire hose fluctuations and they break their magnetic moments. Other ones encounter these magnetic mirrors and they just bounce back and forth inside of the magnetic mirror. And again, they can't maintain resonance with the sound wave because they're just stuck in a trap. This particle initially free streams, trying to maintain the resonance with the sound wave, encounters these fire hose fluctuations and scatters, encounters a mirror and gets trapped, pops out of the mirror, encounters some other fire hose fluctuations and gets scattered, comes down here, gets trapped for a little bit. So none of these particles are able to maintain a Landau resonance with the wave because they're being kicked all over the place. I'm going to skip this. So we did a very thorough investigation of this in scale separation. If you're interested in this, the paper is in Journal of Plasma Physics. We computed the effective collisionality of this plasma. You know, it's a collisionless plasma as far as Coulomb collisions are concerned. But there's an effective collisionality because these particles are scattering off all these magnetic irregularities that the wave has excited. And you can compute that, and you can show that it makes the plasma behave as though it were a fluid, even though it's technically a collisionless plasma. So I'll wrap up. My timer here says I've got 20 seconds. I might go just a few minutes over if that's all right. So we did another experiment. It was a bit of an artificial experiment because we started at t equals 0 with a sound wave. We did another experiment where we just continuously drive sound waves. And you know, if you enjoy stochastic differential equations, this is a really fun problem to solve. This is a linear Vlasov equation. So the distribution function is perturbed. It excites an electrostatic potential. And on the right-hand side, I put a Langevin antenna. So this is a delta correlated antenna, which is just forcing motion in the plasma and randomly exciting sound waves. And you can solve this Langevin problem analytically, and you compute the steady state density fluctuations for a given antenna. And you can show it takes the form of a fluctuation dissipation theorem, where you've got some energy injection and you've got some dissipation. And what we're going to show is that this dissipation rate is affected. It's not the Landau damping rate. It's affected by all the small scale magnetic inhomogeneities, which are spontaneously excited by the plasma kinetics. So you can do that problem. And what you can find is that the collision frequency starts at 0 because it's a collisionless plasma. And then the particles start scattering off of all the excited Larmor scale instabilities. And now the collision frequency is comparable to the wave speed or the wave frequency. You could also look at trapped particles. This particle free streams for a while and then encounters all these scattering sites and gets kicked all over the place. And clearly it cannot maintain a Landau resonance as it's just getting kicked all over the place. We can do things like look at the equation of state. I'm going to go over this quickly, not really explain it. But the point of this is that you can measure the equation of state of this plasma and show that it's not behaving like a collisionless plasma. It's actually behaving exactly like a fluid with the collisionality that we compute. So I'm not going to really explain these slides, but it's just, you can measure the equation of state and show that it behaves as if it were a fluid. Good. So to close, fluid theories of plasmas are broadly utilized in our field and fairly well understood. Unfortunately, a lot of them are not applicable to many space and astrophysical plasmas, namely those that are weakly collisional or collisionless and high beta. So the solar wind, some accretion flows onto black holes, like the one that the Event Horizon Telescope looked at, and the one at the Galactic Center, and the intracluster medium of galaxy clusters. Departures from local thermodynamic equilibrium that are allowed by this weak collisionality are shaped by magnetic fields. They're regulated by Larmor scale instabilities that are triggered. This is important for waves, turbulence, dynamo, reconnection, a whole bunch of things that I could talk about. But just for the purposes of this talk, I hope I said that, just two of the basic building blocks of plasma physics, like an Alfvén wave and an acoustic wave, don't behave as they should. The shear Alfvén waves are interrupted above a beta-dependent amplitude, and the sound waves do not, they shut off their own Landau damping above a beta-dependent amplitude. And interestingly, you've got a direct energy transfer then from the large scale wave directly down to the microscale fluctuations. So normally, like in a fluid, you've got a turbulent cascade that goes scale by scale, but here there's a direct transfer of energy from the large scale into the pressure anisotropy and then down to the small scale with no intermediate cascade. And so what we've been doing based on this kind of work is looking at modern theories of Alfvén wave turbulence, like something called Goldreich-Streethart turbulence, and showing that they don't apply in high beta astrophysical plasmas. So we've been working on a new theory of turbulence in this regime. So thank you very much. I know it's yet another hour on Zoom, so I appreciate it.